Okay, so talking about this rule here in green. Now, we're familiar with this section here, the a to the power of x is equal to y. That's what we've been focusing on with indices. Now, think of logs as the inverse of exponentials. That's the idea behind log. So we have done inverse functions before. When we're focusing on an inverse function for exponentials, effectively that's a log, the inverse. So the easiest way to think of this is the base of the log stays the same. So a is the base of the exponential, but it is also the base of the log. So that little number down the bottom is log to the base of a. Now, what does switch is the power becomes what the log is equal to, and then the y, what your exponential is equal to, is the number of the log. So that's how you're switching around your numbers. Now, sometimes we switch between exponential and log form in order to solve. And that's what we're doing in this first example. So I have log of base 2 of 32. Now, to solve this, what I'm going to do is remember that a to the power of x is equal to y, which is... Now, this double-ended arrow means that they're equivalent, and you can go back and forth between these forms. Log of a, y is equal to x. So I've got the log form at the moment. So I want to put it in my exponential form. So the base is going to stay the same. I'm going to have my base 2. Now, I don't know what this log is equal to, so I'm going to say it's equal to x. Now, remember that what your log is equal to, so equal to x, forms the base of your the power of your exponential. And then whatever the number is here becomes what your exponential is equal to. So we're sort of fiddling around with the numbers. Now, similar to what we were doing last lesson in 13D, where you're solving exponential functions, you're going to do it the same way. So you want them to the same base, so you can equate the powers. So 32 is going to become 2 to the power of 5. And then looking at these two powers together, x is going to be equal to 5. So for this particular one, all we're doing is rearranging it back to the exponential form that we are familiar with and solving. So doing the exact same thing for b, remembering that this log is equal to x, I want to find what it's equal to. So taking my base, same base as the log, to the power of x, because whatever the log is equal to becomes my power, and then I'm going to make it equal to 81. And again, same as we solved in 13D, we're putting 81 with a base of 3, which is 3 to the power of 4. So therefore, x is equal to 4. Okay. These log laws. So log of base a is equal to m times n. That's what's in the bracket there. But now you can go back and forth between all of these rules, by the way, whichever one is more convenient for what you're trying to calculate. So if I have log a of m plus log a of n, I multiply those two numbers. Now remember, this is because these two numbers here come from how we rearrange between the exponential and the logarithm. So these all are quite similar to your index laws. They're just translated into logarithms. So if we have log a of m plus log a of n, we multiply the m and n. Similar to your exponentials, these rules only will work if they have the same base. So these all have a base of a, that's why they work. Okay, similar to the logarithm of a quotient, if we're subtracting two logarithms with the same base, you're dividing m and n. Now, logarithms of a power, this one is a little bit different, still comes from your index laws, but looks a little bit different. If you have a number inside the bracket with a power, that power actually can be multiplied to the front. So if you need, more often than not, you're probably going to be coming from this form to this form here if you're adding two numbers or wanting to add two logarithms. Logarithm of 1 over m, this is pretty much the same thing as log law 3. If you've got 1 over m, remember that this can be written as m to the power of negative 1, because when we have a negative power, we take the reciprocal and we put it on the bottom, and then it becomes the positive power. So all this is doing is undoing the 1 over m and making it a power, and then coming from our third log law, this power is multiplied to the front, which is why that becomes a negative log. It's got that negative 1 that's been multiplied to the front. And then the fifth one, log a of 1 is equal to 0, because remember that anything to the power of 0 is equal to 1. That's why those numbers switched when we've got our logs. And log a of a, so if it's got the same base and the same number, that's also equal to 1. This rule here, weirdly, it's in 13G when we need to use it now. If you have an exponential a to the power of log a of whatever number, so you've got a base with the same log base, that is going to be equal to whatever number is there. So the base a, the exponential a, and the log of a cancel each other out. Effectively, they equal 1, and you get this just whatever power is on the log equaling to. But I will explain that when we get to our examples. So coming to our first example here, we have a couple of logs, looks complicated, looks like it sucks, but it's not too bad. Okay, so we're pretty much going to follow our BODMAS. We have addition and subtraction, which means that I'm going to deal with those first two logs first. Now, just checking that everything has the same base. Everything is to base 10, so I'm good to go with my log laws. So the first two, if there is a number out the front, you can't just add them like adding coefficients. You need to take that coefficient and replace it with the power. So remembering our log law 3, where we have, if we have a p out the front, so a coefficient of the log, that becomes the power on that number in the bracket. So this 2 is going to become the power on 3. So I'm going to have log 10 of 3 squared plus log 10, 16, and I'm going to rewrite this as well. Log 10, 6 over 5 squared. Okay, now dealing with this first, I can only deal with 2 logs at a time. So if I'm adding 2 logs with the same base, I'm multiplying the numbers in the bracket. So I keep my log 10, just like when you're doing your exponentials, the base always stays the same. So I keep that log 10, but what I'm multiplying is 3 squared is 9 times 16 minus log 10 of, I'm going to multiply that out, so 36 over 25. Remember, if I've got 6 over 5 squared, that squared goes to the top and the bottom number. That's from our index laws. That's where our 36 over 25 comes from. So I've got my 9 times 16. Now I've got my one log minus my other log. So this means that I'm dividing the two. Left number goes on top, right number goes on the bottom. So I'm going to have 9 times 16 over 36 over 25. Now, I'm not going to make you guys put that all into a calculator. Once you multiply that all out and divide your 36 over 25, it actually conveniently gives you log 10 of 100. Now, you don't need to do this by calculator. We can still do this by hand. So, does someone want to suggest how I'm going to do it by hand? Yes, Josh? Yes, fantastic. So I'm just rearranging back into an exponential. So 100 can be written as 10 squared. So therefore x is equal to 2. So not too bad. Once we get that number being something convenient for us, we can switch it back into an exponential that we're familiar with and solve that way. Okay, now each of these. Little more complicated. We're stepping it up. So with the first one, we're still switching back between our exponential form. This is still to get us started. So instead of having log 5 of x is equal to 3, I'm going to have, not log, I'm going to have 5 to the power of 3, because remember the number that it's equal to is the power, is equal to x. Now 5 to the power of 3 is 125, so 125 is equal to x. So that one's not too bad, just a little bit different from the examples we've been doing. Now, coming over to b, I now have a log that is not just a number. So I have log of 2x plus 1 is equal to 2. Okay, now this is where this last log law comes in that I've got in black. Even if I rearrange this, it's still not going to work out nicely for me. So the easiest way that I would, actually no, let's rearrange. So that 2x plus 1 becomes what my exponential is equal to. As per usual, 5 is the base and 2 is the power. So I have 5 squared is equal to 2x plus 1. No? So this number, whatever is in that bracket becomes what my exponential is equal to, even if it is a linear equation. Then I have my power being 2. So I've got 25 is equal to 2x plus 1. Then I'm going to solve as per normal. Minus 1 to the other side. So I'm going to have 24 is equal to 2x. Divide both sides by 2. I'm going to get 12 is equal to x. Okay. Now I've got C. I've got 2 logs, log 2x plus 1 minus log 2x plus minus 1 is equal to 4. Okay, does someone want to suggest how I'm going to get started? Which log law would I be using first? I've got the same base, which means I can use a log law. Yes, fantastic. I'm going to use my second log law. So I'm going to, when I'm minusing 2 logs, I'm dividing the 2 numbers. So I'm going to have log 2, 2x plus 1 on top, divided by x minus 1 on the bottom is equal to 4. Now that I've got it into one log, I can do my rearranging back into an exponential. So 2, same base stays, to the power of 4, what it's equal to becomes the power, and then it's equal to 2x plus 1 over x minus 1. So 2 to the power of 4 becomes 16. That's going to be my first thing that I'm going to get rid of, x minus 1, and then I'm just going to do some solving. I'm going to multiply both sides by x minus 1 to get rid of that fraction, and multiply out the bracket. I'm just going to collect my like terms on either side, and then I'm going to divide by 14. So I'm going to get 17 over 14. Okay, last but not least, I've got D. So log 3x minus 1 plus log 3x plus 1 is equal to 1. Now, always checking that I've got the same base. Same with exponentials. I've got the same base. I'm good to go. So I'm plussing them, which means I'm going to do what to the 2 numbers in the brackets? Multiply. Good. So I've got log 3 x minus 1 x plus 1 is equal to 1. Now, what have I got inside that bracket there? What do I call that x minus 1, x plus 1? Difference of 2 squares? Yes, fantastic. So I'm going to have x squared minus 1, because where a squared minus b squared is the rule, is equal to 1. Now, same as per usual, I'm going to rearrange. Base stays the same. power is 1, so I'm not going to write the power, is equal to x squared minus 1. I'm going to plus 1 to the other side, which gives me 4 equals x squared. Square rooting both sides, I'm going to get plus or minus 2 is equal to x. So